All right, I'm back and I've got maybe bad news again. I I didn't hit okay enough times on the previous render and it says I couldn't save the next one, and I'll talk to the people at Zoom because it's there. I just can't render it. Excuses, excuses. You'll get something for segment 2, but it won't be today. Moving on to our next segment. We're going to do the reaction that took our alkyne, which was right here. That's not nice. And reacted it with Hg2 plus with a sulfate ion. I'm going to redraw the sulfate ion like this. And we have water. And we have sulfuric acid. And we're going to make that into butanone. First step, we attack the mercury 2 plus ion with our alkyne, and we make it into a cyclic mercurinium ion. This one has triangles all the way around. When I said all the way around, I should have gone all the way around. Yep. This triangle is 3 partial bonds. That is, it has a total of 2 electrons. And we're going to do a backside attack on the least hindered. No, I keep saying that, don't I? This is a cation. When you do backside attacks on triangles that have cations in them, it's all about cation stability. Easy to remember. If you see a cation, it's about cation stability. If you don't see a cation, it's usually about steric hindrance. So I'm a little rusty talking about these things too. So we're going to go for the more substituted carbon. That's good news because my product right here has the O on the more substituted carbon. And this comes in from behind.
Dr. Whitaker?
Yes.
I was
Audio?
wondering,
Yeah.
yes, I was wondering if you can do this in a separate page.
On a separate page. Sure.
Thank you.
Let's copy it to another page. It might be a little messy, but we'll be able to tidy it up. Oh, that's, well, we'll see. Let's go to a new page. And get rid of all of our extra stuff on the bottom here. There we go. And we've got, nope, H there. And we're popping open our triangle. And we're going to have this. Water came in from the bottom. It's got an oxonium on it. Same carbon has an ethyl, which got pushed upwards. Mercury has all those electrons that used to be in the partial bonds, ended up in this one real bond. So the whole triangle, all the electrons, when this attack happens, shifted over to there. So 2 electrons here where there used to be 2 electrons all the way around. And we have an oxonium, which needs to be neutralized. We'll do this mechanism in a circle. How's that? In case you're wondering where we started here. And we'll come around to this ketone here. So our best base that we have right now is sulfate ion. And without having arrows cross things, let's just redraw the sulfate ion. I thought I was smart drawing it out earlier, but you know, logistics often change. Got a minus there. One of the O's needs a lone pair. There's a minus in there. Grabbing one of the oxonium H's. O becomes neutral. And now we have this alkene that has an ethyl up here and an OH here. There we go. And let's see, is that what we have? Yeah, and we have hydrogen sulfate ion, which we can use later at our discretion. It's now our best base for future use. And we have this alkene that has an alcohol on it. That's an enol. That will do tautomerization at the end. But right now we need to get rid of the carbon-mercury bond and replace it with a carbon-hydrogen bond. Remember, carbon attached to a metal is an anionic type carbon, isn't it? So I need a cationic type hydrogen, and the candidate that best fits the bill is sulfuric acid. So we'll have sulfuric acid up here, which we have yet to use. I still am fascinated by this mechanism that illustrates how reactive mercury is, in that mercury reacts before sulfuric acid. You don't see that very often. Sulfuric acid's a very strong acid. Oh, it ignored me. And there we go. Acid base protonolysis. We made Hg2 plus. Which if you look back, we started with Hg2 plus. That makes Hg2 plus a catalyst. And we now have a straight up enol. On the more substituted carbon, which needs to undergo tautomerization like our previous reaction. And tautomerization always requires an acid-base pair. And earlier I mentioned this would be our best base. Its conjugate partner would be the best acid. And I will put it, I'm going to put it right beside it. It needs to provide a proton on the left carbon here so that it can become a CH3 right here. That used to be a CH2 right here. Tautomerization again. Tautomerization requires the base to grab the H. Sigma becomes pi. Alkene picks up a proton on the end from the acid in the conjugate base pair. Make sure that arrow starts in the middle of a bond. And there you have the ketone that you made by starting here and following all the steps around. We can number them so it's a little clearer. And just describe each step a little bit. Step one was the attack on the mercury 2 plus cation to make the mercurinium ion. Step 2 was an acid-base reaction to neutralize the oxonium. Step 3 was protonolysis. And step 4 was our tautomerization, giving our ketone, useful functional group, the ketone. So let's see what we have on page 2. We've done the mechanism across. We did the mechanism for these two. Let's finish our mechanisms with, let's see, we got all this stuff here. See what we can do. And we're going to snip. Where are you, Snippy? There we go. So we got our butine. And everything here. And I think I have a way to make Miss Fanoff a little happier. I'm going to do a pause for a second. Hope I don't start before unpausing. Minimize this. Go to the end here. New page. All right, what don't we need here? We don't need that. We're here. Did we do this one? I don't think so. Get rid of the butanone, the mercury. Oh, almost got rid of something I need. Dangerous eraser. Okay. One butane. All right, we're going to start the video again. We're going to do the mechanism where we take one butane, take its H off, do an SN2 to make this here. And let's do that right here, right now. Put this here. And this here. Okay. Don't need any of this on this page. Okay. Start here. Got an H on here. And the H is going to lose. It's going to be taken by a strong base.
Doctor,
Yes.
you're not sharing the screen with us.
I'm not what?
You're not sharing the screen.
Oh, that's very selfish of me, isn't it? Here we go. That's good. We're going to start the video again. Now I'm sharing the screen, right? Thanks for doing that. We got our start here. And we're going to take the H off with H negative right here. I crossed off the spectator. And we're going to make acetylide that has an ethyl on it. You can call that ethyl acetylide. And it's going to attack benzyl bromide. Backside attack. Leaving group leaves. Synthesis accomplished. We got a new bond right there. We've got acetylene with an ethyl right there. And that's this one right here. So we got two copies. We got the one here, and we have the one here. We can do the sodium and ammonia on the left. Remember, sodium is in the family of molecules called radicals. Or it's an atom that's called a radical. It's got an unpaired electron. Yeah, let's see. I see a little dot there that's disturbing me. I got a way to make a radical that's better. Yes. Okay. Radicals, you can't use arrows with radicals. You remember that? You have to use hooks. And hooks go like this. We're going to put one of the hooks to this carbon here. And the pi is going to break and become a lone pair on the same carbon. And the other pi is going to break, same pi is going to go halfway to the other carbon. So in terms of the pi bond, it's being broken equally in half. We call it homolysis. Don't worry about that word. Half going here, half going there. That's going to be lone pair. And if you review formal charges, a carbon with a lone pair and 3 sigma bonds has an anionic charge. Carbon with simple radical has no charge. It owns half of that, half of that, half of that, and all of that. That's 4. Here, the carbon owns both of those. Half that, half that, half that is 5. That's an anion. That anion is the conjugate base of an alkene, which you know is a very, very strong base. Second strongest base you know. What's going to provide a proton to protonate that base? NH3 is listed over the arrow. It's both the solvent and a proton for this reaction. Remember, its pKa is 40, like an amine. So it's going to provide the proton. And you get lone pair here. No, there's no lone pair there. We just use the lone pair to make a bond. You get an H there. And you have a radical underneath. How do you get the second H on there? Well, let's ask the question, how did you get the first H on there? Here's where we put the first H on, using a lone pair from a alkene anion. Well, let's get an alkene anion down here now. How do you do that? Needs to be a lone pair. Needs one more electron to be a lone pair. So yes, sodium metal is in excess, at least 2 moles sodium metal for this reaction. And now you have an anion, which you can protonate. Like you did before. Anion. And we're going to make that into this. I notice I didn't copy all of phenyl. No, I think that was my crazy eraser getting out of hand. There we go. How do we put a second H on there? Well, how did you put the first H on there? Your ammonia solvent is also your proton source. Lone pair protonates. The BH3 reaction is much simpler than this. This was a chapter 7 reaction. They're both chapter 7 in the same area because they're both reductions of alkynes. We'll start on this molecule. We don't need hardly any room here at all. BH3, I will redraw right here. And this one's back to normal arrows for mechanisms. And we're going to react with the boron before the hydrogen because boron's more positive. And at the same time, the hydrogen comes back to one of the carbons. I don't like that arrow, didn't hit the carbon. And now my thing's ignoring me because my pen's off. Yeah. There. So what we made here was a carbon bonded to boron on one side. Looks like it would have to be the left side using the arrows I used up there. Boron with 2 H's on this side. New H on the other side. And now the role of acetic acid is this is acetic acid right here. The role of acetic acid is much the same as sulfuric acid was with the mercury. It will do what's called protonolysis. Use the acid to replace a carbon metal bond with a carbon hydrogen bond. And here is acetic acid. Acetic acid, carbon boron bond becomes carbon hydrogen. And an optional thing to show in purple would be the formation of H2B OAC. And here's where we can use our new knowledge to save time. Red was first, blue is second. Boron lost a bond, and it got it back in a second step. Now O is bonded to boron. So simple one. That one only has 2 steps. Hydroboration followed by protonolysis gives that result there. Okay. So not too messy. I think we're almost finished with our mechanisms. We did those. And what we didn't do is the sodium ammonia. I'm not going to do sodium ammonia again because we did that one, but we can tackle everything along here and do that on the next page. There's the next one. I guess this is the last page. We might have the same thing twice. So let's get rid of some stuff we don't need. I'm going to start with the 1-butene. Okay. Moving everything on up. Okay, here we have peracetic acid. We can do that mechanism or this one. I'll let you review the bottom one. Let's do the peracetic acid. That was a fairly new one we learned at the end of 241. We need to draw our peracetic acid like this. It's per means 1 extra oxygen. Per is consistent in chemistry to mean 1 more of something. And in this reaction, we want to break the OO bond because that's what's the least stable part of peracetic acid or any acid. So we attack the O that's furthest from the carbonyl. I believe we call that the distal oxygen to the carbonyl. Don't attack the proximal one. The arrows won't work. And then you resonate this. You're going to get a new carbonyl. This O is going to grab a bond to the H. Going to have crossing arrows. So let's just change the color slightly. Here, two colors doesn't mean two steps. I just want you to know the pink and the red are different. And then the last one, this bond goes to the more substituted carbon. And you get your epoxide. And if you're curious what happened to the peracetic acid, here it is. Once again, it's a side product. It looks like the carbonyl is now here. CH3 here. The O now has an H here. And it's acetic acid. And we made an epoxide, useful synthetic tool epoxides. Okay, and the epoxide is going to be popped open. This time we're opening a triangle that does not have a positive charge. It's not about carbocation stability, it's about approachability. Which carbon is easier to approach? The one that has only one more bond to carbon and a bond to oxygen, or the one that has two bonds to carbon and a bond to oxygen? I think the answer is the one bond to carbon. And here's the mechanism. It's a pretty simple one. And I'll make a comment about combining steps when I'm done here. Some of you want to say, okay, I'm going to put that H on there right now. I'm going to put a lone pair on this O and then use a different color arrow and grab this H. You can't do that. It's inappropriate. You're not acknowledging that they actually have to be done in separate steps. You have to make sure reaction 1 is done and show me the result before you even start reaction 2. So whenever I have step 1, step 2, you can't combine something happening in step 2 with something happening in step 1. I hope that was clear. And so step 1, we're going up here. You've got your alkyne. You got your exciting new bond here to a C that's a CH2, and it goes to a C that has an O minus. And it has an ethyl on the same C. To make sure we have the right number of carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Good. Now step 2 is performed after this reaction's over. I believe I have some lab students right now who finished step 1 on Tuesday, and then they did step 2 on Tuesday too, but they definitely did it separate. They were dropping 3 molar HCl into the reaction after they finished the first step. And here's what was happening for them, although it was a different reaction slightly. Acid base. Oh. Okay. We have an OH. We protonated our oxygen and we have an alcohol. PCC mechanism we're not responsible for. And we did already earlier today the HB-Sia2 KOH H2O2. So we're not going to do that. This would be a logical stop in this one. And I've learned lots of lessons. as we've been going, I've been thinking there's got to be something different about the setup I have for the 242 lectures and the 241, because theirs show up on the spot on my computer and yours don't, and I have to talk to Zoom. There's some setting I did wrong. You're my guinea pigs. I apologize. So we're going to have another segment after this, and so stay tuned. This one's short, so 5 minutes. I'll make sure I hit all the OKs I'm supposed to hit, and we'll be done with this segment. Coming back 5 minutes. So stopping, saying goodbye, ending.